So let's do some problems involving two-dimensional equilibrium problems. So the first problem is a sine problem. So we're told that a 1000 Newton sine hangs on a 1.5 meter long rod which has a weight of 250 newtons. So we're told then that, sorry, not the mass, the weight of the sine is 1000 newtons. So that's already the force. We don't have to do mg if it tells us the weight in newtons, and the weight of the rod is 250 newtons. The rod is attached to the building at one end, and at the other end it's supported by a cable at 40 degrees to the horizontal. So remember, the first step is draw a picture. So let's draw a picture. Here's our rod attached to the wall and it has a cable on it, and the cable's at 40 degrees. Okay. The sign is hung 1 meter from the wall. So this rod is 1.5 meters long and my sign is hanging 1 meter. And I want to find the tension in the cable and the forces exerted on the rod by the wall. So let me draw my forces on here. So I've got the force of the tension in the cable. I've got the weight of the sign. And the weight of the sign acts 1 meter from the wall, we're told. So let's call that R sign. What else do we have? We've got the weight of the rod. Where does the weight of the rod act? It acts halfway along the rod. And since the rod is 1.5 meters long, that distance is called R for the rod is 0.75 meters. If you can see that in there, that's R for the rod. Let me write that up here. R for the rod is 1.5 over 2, or 0.75 meters. Okay, and what else do we have? We've got the force of the tension, which we don't know. We're trying to find it. And we've got forces from the wall, and the wall will have a vertical force that's called the FV that keeps the rod from sliding down the wall, and it's also going to have a horizontal force that keeps the rod from pushing through the wall. You could imagine if the wall were made out of paper, that rod would just push through the paper and swing over towards the left. So we have three forces that we don't know and that we're asked to find. Okay, so how do we do it? Well, we've drawn a picture showing all the forces. The next step is to say the net force in the x direction is equal to 0 and the net force in the y direction is equal to 0. So let's look at what forces we have that are horizontal. Well, we've got FH from the wall, and that's going to the right, so we'll make it positive. And let's see, the FV is vertical, weight of the rod is vertical, weight of the sign is vertical. So the only other force that we can have is the x component of the tension. So if I draw a picture of the force of tension, this is 40 degrees. FTX and FTY are the vertical and horizontal components of it. So FTX, that side, the horizontal side, is adjacent, so that's going to be FT cosine of 40, and it's in the minus x direction because it's going towards the left, and FTY is going to be FT sine of 40 because that side is opposite to the angle, and it's going upwards, so that's going to be positive. All right, so I'm going to have FH minus FT cosine 40 equals 0, so that means that FH is equal to FT cosine 40. Okay, so we don't know FH and we don't know FT, but you can see that using this equation, and let's call this equation 1, using that equation, if I know FH, I can get FT or vice versa. Okay, what do we have in the y direction? So in the y direction, we've got FV up. We've got the y component of the tension up, FT sine 40 up. And then we've got the weight of the sign down and the weight of the rod down. So FV, which we don't know, plus FT sine 40 minus 1,000 minus 250 equals 0. So if I simplify that, FV plus FT sine 40 is equal to 1,250. All right, so that's equation 2. All right, so again, now if I found, say, the tension force, I'd be able to find what the vertical force is. So I've got 2 equations. I need 3 equations to solve for 3 unknowns. So I'm going to have to go and do the tension. Sorry, the torque. So to do the torques, I have to set my axis at a location where I have forces that I don't know. So there's 2 places that it could be. One could be at the wall, and one could be at the end of the rod where the cable is attached. I'm going to put it at the wall because I've got 2 unknown forces there, and that'll simplify things for me. So if I put my axis at the wall, then that means that the torque due to the vertical force will be 0, and the torque due to the horizontal force will be 0. Why? Because they're 0 distance from the axis, and so the torque will be 0. So now I have to find the torque due to the other 3 forces. So I've got torque due to the weight of the rod, I've got the torque due to the weight of the sine, and I've got the torque due to the force of tension. All right, so 3 torques, and those together will have to add up to 0. All right, so torque from the rod is going to be the force of the rod, which is 250 newtons, times the distance that it is away from the axis. And here, since my axis is at the wall, the weight of the rod is acting halfway along, so that's 0.75 meters. Okay, the torque from the sine is going to be the force of the sine, 1,000, acting 1 meter from the wall. And the torque of the tension is going to be the force of tension, which I don't know, times the distance that the string is attached from the wall, and we're told that's the whole length of the rod, 1.5 meters. And now I need to worry about, remember, torque is FR sine theta. What's my angles? Well, for the weight of the rod and the weight of the sine, those are perpendicular to the rod, so that's going to be sine of 90. For the tension, that force is 40 degrees to the rod, so I'm going to do sine of 40. All right, so now I can plug that into my calculator and calculate the numbers. So the torque from the rod is 187.5 Newton meters. The torque from the sine is 1,000 Newton meters. And the torque from the tension, well, I don't know the force of tension, so I can only do 1.5 times sine of 40. I get 0.9642 times whatever the force of tension is, Newton meters. Okay, so the net torque has to be equal to 0. And in order for that to be equal to 0, some of these have to be positive, some of them have to be negative. So how do I figure it out? Well, what I do is I take my pencil, I put it on the sheet of paper where the rod is, I hold it where the axis is, so that's at the left end. So now if I pull down on it the way that the weight of the rod and the weight of the sine is, those will make the pencil rotate in the clockwise direction. So those are going to be negative torques. Okay, so those are clockwise and clockwise. What about the weight of tension? Well, if I pull up on the end of the rod, that's going to make it rotate counterclockwise. So that's going to be a positive. All right, so what I know is that 0.9642 times the force of the tension minus 187.5 minus 1,000 equals 0. So 0.9642 FT is equal to, if I add the 2 numbers over the other side, 1187.5. So the force of tension is equal to 1187.5 over 0.9642, which gives me 1231.2 newtons. Okay, so now remember I said that once I found the force of tension, I could plug it into equation 1 and equation 2 to give me the other two forces that I need to know. So let's do that. Okay, so if I look at equation 1, back to green, equation 1 said that the horizontal force was Ft cosine 40. So that's 1231.2 cos 40. So that gives me 943.5 newtons. And equation 2 told me that Fv plus Ft sine 40, so plus 1231.2 sine of 40 equals 1250. So that gives me that the vertical force, if I plug all that in my calculator, is 458.6 newtons. Okay, so now I've got numbers for the three unknown forces. The last step is to go back and look at the number and check the sig figs. It looks like I've got two significant figures and everything, so I should round these guys off to 1200 newtons for Ft, 940 newtons for Fh, and 460 newtons for Fv. Okay, so hopefully that sign problem made sense, and you should go back and calculate